Now notice that these terms are no longer dependent on x and y, so I can take them out. In fact, let me collect terms in the exponent. That's 2 to the minus n h of x plus h of y minus 2 epsilon. That's the sum over the typical set of 1. So therefore this term, this sum, that's equal to the cardinality of the typical set. Now a second ago I showed that the cardinality of the typical set is upper bounded by bounded by 2 to the n h x and y jointly plus epsilon. So this is equal to 2 to the minus n. If I take out a minus n from here, I get 2 to the minus n h of x plus h of y minus h of x and y minus 3 epsilon. What is this? Mutual information. Which is equal to 2 to the minus n mutual information minus 3 epsilon. So that's the upper bound. The lower bound is proved much the same way. What I can do is I can say that sum is greater than or equal to the cardinality of the typical set times the lower bounds over here, 2 to the minus n h of x plus h of y plus 2 epsilon. And then I can substitute the lower bound for the cardinality of the typical set in there, which is 1 plus epsilon 2 to the n h of x and y jointly minus epsilon times 2 to this term, which is equal to 1 plus epsilon 2 to the minus n I of x and y minus, plus 3 epsilon. So that's interesting. Once again, if you select x and y the way they're supposed to be selected, the probability of them being in the typical set is 1. If you select them, independently, then the probability that they're in the typical set is somewhere around 2 to the minus n times the mutual information. So, effectively, you could argue, so again, let's come back to the possibility of random coding. So what we're going to do is we're going to assign each message, when we end up proving the channel coding theorem, what we're going to end up doing is we're going to assign each message a random code, a randomly selected code word. So that means that if y is the channel output corresponding to x, then they're dependent, and if y, and so therefore they should be jointly typical. And if y is not the output corresponding to the input x, then they should be independent. So in some sense, what's going on here is that the probability of an error occurring should probably be somewhere around 2 to the minus ni x and y. what that furthermore means is that if the number of things that I can be confused with is less than 2 to the minus n types of mutual information, I can force this probability of error basically down to 0 by picking n sufficiently large. This probability is going to go to 0 as n goes to infinity. So basically, here is the sketch of the argument going forward. This is roughly the probability of error. So if the number of things I can be in error with is less than this, then the probability of error will probably go to 0. Basically, the argument would be, this is the probability of error between a sequence and something that was not transmitted. So therefore, the maximum number of such sequences that I can have and still have this probability go to 0 is around 2 to the n I of x and y. Or as long as that's less than this, then I'm okay. So what that implies is that this should be my rate. If I take log 2 of this expression, my rate should be around I, x, and y. So that's a very quick argument. We're going to go through that in more detail, but it's helpful to see this as being approximately the probability of error, and therefore, as I pack more and more code words in, there's potential for more and more errors, and so therefore, ultimately, obviously, there will be a limit beyond which I can't go, and that limit should probably be expressed by this term. The maximum number of things that I can have and still be able to force this probability of error to 0. Okay, what I'm going to start this now. What I'm going to do is I'm going to describe the I'm going to describe the transmitter-receiver setup to prove the channel coding